All right, so we're looking now at chapter 14 in SolKind. Um, and this is about analysis of variance when you have more than one factor. So uh, think back to the uh, um, last assignment, last ANOVA. We had one grouping variable, which was the the uh, the intervention group that they were in. It had three levels, less than 15, 15 to 25, or 25, but there was only one grouping level. So this example, which comes right out of the text, has two grouping variables. So we have the grouping variable of male, female, which should actually be called gender, and then we have the grouping variable of being in the high impact group or being in the low impact group. So uh, pretty straightforward to do this in Excel using your data analysis tool pack. You just grab your two-factor with ANOVA two-factor with replication, click OK. You select your data range. That's just all of the data that you want to include. Click OK. And then you got to insert the number of rows per sample. So in this case, I have male 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. So I've got 10 variables in each one of those groups. Now that is a bit of a limitation, and I'll put it over here in this new tabbed name. That's one of the limitations of Excel, is that if I had 11 females in that group, well, I'm sorry. It just wouldn't work. You'd have to cut somebody out, and how are you going to decide that? So a little bit of problem with the way Excel works. And so, but anyway, we'll quickly go through that and click OK, and we get almost instantaneous answers. We'll go ahead and reduce our decimal points down to something a little bit more visually understandable. Okay, we can see we've got more data. We have our data broken up into different ranges, where we have the count of males. We have 10 of them in the high impact, 10 in the low impact. We get the average for the high impact males. We get the average for low impact males. It's also broken down into females. Again, the count, 10 and 10, and then the average for high and low impact. And then we have that all totaled up. So that's nice. And then we come down here and we have several ANOVAs to deal with. And so, where was I at? So we have our F values here that we're interested in, and Excel, as it always seems to want to do, gives us the critical values for no extra charge, so we don't have to go rushing back into our tables to find those, and so that's a good thing. About the output, this where it has sample, it refers to these items here. So we have gender, male and female. So this sample here is really going to be our gender. Where it says columns, that's pretty obvious what that means. It means these two impact levels. And and when it says the interaction, it's going to be the interaction of male and female with the columns. So that's how we look at that. And so let's look at the F scores for our sample for the gender two variables, and we can see that our F score does not exceed our F critical for gender. So we kind of think overall there's no difference between males and females when it comes to their variance in their outcome. So in the columns, and this will be comparing the two columns, and again we have no difference because our F score doesn't exceed our F critical. But we see down here in the interaction, and so what the interaction is the when we look at all of the variants together, the effect of gender and the effect of the type of impact, level of impact, high or low, that we do see some value differences. And so we have an F score that exceeds our critical value, but we don't really know where that difference is going to lie. So it's going to require some more testing. So all right, let's take a quick look at how to do this in R. And where's my R at? So for time's sake, I went ahead and imported the data into R. Called it impact. Doing the analysis in R is let me go ahead and get rid of my old stuff here. Get some fresh stuff here. All right, so my data set, which looks like it has a whole lot of extra columns in it that I don't really need because it doesn't have any data in it anyway. I've got my my data put into R, and in order to get it into R, I had to reorder things. So I had to change the gender around and add a column for level of impact. So there's a little manipulation that one must do in Excel to get that to work. So I had to make it look like this versus versus what it looked like originally. And this is quite often more like what you'll get it in. And so there's always going to have to be some kind of monkeying around with the data in order to get that to work. So so let's go ahead and just take a quick look at our statistics, our multi-way ANOVA, where we've got gender and level. Select both of those. Click OK. Our response variable is already picked. And because we have so few cases, we're getting some NAs in here, but we can ignore that. And R gives us our variable names, so we can look at the values more directly, and we can see that they're just the same. We got the 0.968, just like we had before um, in in our previous ANOVA, 0.968. Probability value of 4, 0.004 is actually 0.0036. That's what we got in R. We got these other two values, F values of 1.9 and 2.4. So we're getting the same results, and not significant on gender, not significant on um, um, the level of impact or the type of impact. So again, like we did earlier, we can use our QF function to to do a 0.95 critical value for our F score. We had 1 degree of freedom, and we've got 36 degrees of freedom in our residual. We can hit submit, and we see we get the critical value of 4.11, just like we did in Excel. So we are super good to go. We can say that the interaction of gender and level of impact is makes a difference. So we'd want to kind of drill down into some of these values. So we can see that females who have low impact are really the outliers. So they scored 64 versus females who with high impact who scored 79, actually higher than either males with high impact or males with low impact. We can also see we've got kind of an odd set of data here where we've got males who have a higher low impact score than they did on their high impact score, and so we've got this reverse. So we've got some kind of curious data here that we would probably understand a little bit better if we knew the context of what we were studying. So you know, the way the world is, we often don't get data that has, you know, perfectly leveled. I mean, sometimes when we're doing research, of course we can manipulate things, but you know, sometimes we'll have data that has a whole lot more variables, and sometimes they're not going to be even. So we can see that in this particular example, it's cut and paste from the same data, that we have more low impact scores than we do high impact scores. So maybe say if this is aerobics and these are strength scores or strength improvement scores or something like that, we have perhaps we have more people who are willing to take the low impact classes. So let me go ahead and import that into R, and you notice I had that in a CSV file. So let me just go ahead and import that. Call that impact more. Why not? It's got commas. It's in our local file system. I said okay. And no, that's ooh, which one was it? All right, Bob. Got to remember the names of your import XLS. All right. Oh, that's an XLS file. Oh, that's why I couldn't find it. Okay. Hold on. Let me cancel out of there, and we'll just import this using our import from Excel file. Impact 2, we'll call it. And open up that bad boy. It's reading that level. Come on, I need to see a... Oh, it only had one worksheet, so I didn't need to do anything else. So view my data set. All very good. Do a quick summary statistics. We can see we've got 26 females, 30 males, 20 in the high impact, 36 in the low impact. So our other impact had oh, we got all that junk in there. We've got 20 and 20. We've got 20 and 20. So we've got two different sets of data here. I mean, they're not equal. We can still do our analysis of variance on gender and impact just the way we did before, and we can see that we get a little different scores because we've got more cases. So our gender plus by impact is still the only thing that is really significant in this equation. It doesn't surprise me. It really is the same data, but it's just a little bit different. Let's do our QF function. We've got 0.95 confidence level. We've got 1 degree of freedom on our numerators. We have 3 numerators, and actually you can write this way. You can put a small c, which stands for concatenate, and then you can do 1, 1, 1, and then put another comma, and then you put your numerator degree of freedom, which is 52, and it'll just give you the same number 3 different times. So our critical value for this one is going to be 4.02. So it's a little bit different. Again, our first 2 test does not exceed that amount. So we put the big thumbs down. But it does for the F value for the interaction of impact and gender. So we say we have a good test. We have really no difference between the type of treatments, no difference between genders, but we're going to want to target genders depending on impact level. So let's look down in here. Come on, you slide around a little too much. Sorry about that, everybody. So we have our means of impact by gender type. So we've got again a situation where we've got low means for our females on the low impact. We got higher means for the females on the high impact. Males are looking at getting lower scores on the low impact. I mean higher scores on the low impact, and then lower scores on the high impact. So clinically, if I was wanting to assign people, I would say, oh, it looks like we probably need to be sending females over into this high impact group, and the males over into this low impact group, because that's where they seem to do the best. Although it's at this point it's difficult to say that there's a difference between high and low impact for males. So we'd have to do some more analysis. We might want to cut the females out of this analysis and just compare the males by themselves, and see how that works. So that there may be some more work to do. So and we would do that with just a simple t-test. So we could go back, edit our data to get the males and females separated out, and then check them for an effect. So I'll do that in just a second. All right, so let me get my data in here. My new data. I've taken my file and manipulated it around a little bit. So we'll just call it follow-up T. And I should have a thing in here called follow-up t-test. I have it right there. 10 rows in 4 columns. The way I set it up, I just put the male high impact, male low impact together, female high impact, female low impact. Take the next step, go to our statistics, to our now we have a situation here where we want to do a independent samples t-test, because this is not test retest, but our R commander doesn't give us the option to have that when our data is set up this way, but we can coerce it into doing that. So let's take a look at our process. So we want to do our females, check females against females, click OK, and see we get this paired t-test, but we don't want to do a paired t-test. We want to do independent samples. And so where it says paired over here, all we have to do is come in and change that from true to false, and then we can hit our submit again, and we get the Welch 2 sample t-test. And we can see that the females are indeed different on these two groups. And then we just do the process again for the males. So we have to go over that paired paired thing again. We've got to change it to false, and you have to capitalize false entirely. Although I think you can do just capital F, right? You can just do the capital F and get rid of this stuff, call it junk. And we can see with the males that there is no statistical difference. So it doesn't matter which group we send the males to, because they don't seem to change with this intervention. So this intervention may in fact only be for the ladies. So doing our critical values, again, instead of QF, it's going to be QT. 0.95 is our thing. We've got our probability value, our degrees of freedom. Where's our degrees of freedom? Oh, right there. We've got 14.79 degrees of freedom. That's really going to be 15 degrees of freedom. And it'll give us a 1.75 um, 1.75 critical value for that was for the males. Now we'd have to do it for the females. That they had more females were in there. They had 18 degrees of freedom. Not going to be that much different. Females 1.73. So the males did not exceed their critical value. That's why they have a non-significant test, and so that's just our process of going from an analysis of variance, a multifactorial analysis of variance, and then teasing out the difference using R. And you know, if you really insist on using Excel for this, oh, I did want to open my mail. Let you see all my spam. Let me come to my remote desktop over here. So this is set up to do t-tests, data analysis, t-test assuming equal variance. We got variable range 1. We got variable range 2. We do have labels, and let's just put it right below it here. Click OK. Repeat the process for our for the ladies. Female impact, female high impact versus female low impact. And we'll put our output right underneath the female output and click OK. And we should have, and we do two tails, F critical, the F statistic does exceed. We got a good probability value, and we have a situation where we do not exceed the critical values with our t statistics for the males. So we get the same results, equal easy to use. It just means you have to move your data around a little bit before you can do your test, and it's part of the price of being a smarty pants researcher. So, all right, that's enough for right now. Probably too much. About 3/4 of you are saying at this point.